This is section 3.9, related rates. We're using an application of differentiation, in particular implicit differentiation, a bit more applied as opposed to theoretical like we did with linear approximation. There are word problems, which always adds an extra bit of ambiguity, but they're still quite formulaic. Let's take a look at how to solve them. Pause the video and read example 1. We don't need to draw a picture for this one, but it doesn't hurt. We've got a beach ball, something like that. We've got a radius, r, and of course the whole volume, v. And what do we know? Well, I guess we know that the volume changes with respect to time at a rate of 40 centimeters cubed per second, right? Cubed because it's volume, right? And we also see that we're trying to find the rate at which the radius changes with respect to time. And note, of course, that whatever that rate is, it's going to be measured in centimeters per second, right? So that is what we're really trying to find. Okay? So the way that we solve the problem is in the following steps. Step 1, write the relevant formula. Now in our case, we see that the volume of the sphere is related to the radius of the sphere. So we write the formula that relates the volume and the radius of a sphere, or a ball. All right, well that, we should know, is 4/3 pi r cubed. Yes, we know that, I should say yes, if I give this to you on a quiz or a test, I will tell you the formula, even though we all should know the formula of the sphere, right? Step 2, implicitly differentiate on just the formula, usually with respect to time. With respect to time. Okay? So let's see what that looks like. If we differentiate v with respect to time, then we get dv over dt equals, and then we get 4/3 pi, and then it's going to be 3r squared dr over dt. Right? Because we're differentiating with respect to t, not with respect to r. Right? And just note, of course, that in this case we can, simplify. Make it a little bit nicer. Always good to simplify if you see a simplification that makes your expression easier to look at, right? Okay, step 3 is going to be solve for whatever you're looking for. In this case, it's going to be dr over dt. So all I'm going to do is divide this stuff over to that side, right? Or just be clear, over to that side, right? So we get dr over dt equals dv over dt times 1 over 4 pi r squared. Okay? And then last is step 4, which is plug in the known values. So when we do that, we're going to get, well, first of all, let me just copy and paste this guy over because I'm just literally using the same thing. And in fact, you can just go ahead and skip right from 3 to 4 if and when you're used to doing this, right? You know, it's like enumerate these. Anyway, we're just going to use this notation. R equals 7, right? And dv over dt equals 40. Now, where do we get those from? We got them from here. Volume increases at this rate. Radius is 7, right? That's where we're interested in finding things out, right? Let me move that up a little bit. There we go. Right? So that's the notation, right? And when we plug this in, we get 40 times 1 over 4 pi times 7 squared. right? And just with a bit of simplification, you can see that that's going to go to 10 over 49 pi centimeters per second. And that is the answer. Now, just want to point out again that the reason we started with this volume formula in general is because the rate of increase of the volume affected the rate of increase of the ball's radius. Hence the term related rates, right? Because the rate of increase of the radius depends on the rate of increase of volume. Now, we didn't really need to draw a picture in that case, but sometimes we might. Sometimes it helps us visualize what's going on. That last example was pretty easy because all we really needed to worry about was the sphere's radius. We had the sphere's volume and the sphere's radius. That's it. What if we had something a little more complicated? Pause the video and read example 2. Now I'm drawing example 2. Whoop. Let's try that again. Let's just do something like this, right? And suppose we've got a 10-foot ladder. Okay, now if the distance is changing, I'm not going to write a number, but because the ladder is always 10 feet, I will write 10. But for example, the distance between the bottom of the ladder and the wall is changing. That's going to be x. The distance between the top of the ladder and the floor, that is changing. I'll call that y. You can call it like b for base and h for height if you want. But anyway, this is our situation. We know that dx over dt equals 2, right? From this guy. Maybe that's worth just highlighting really quickly. Okay. What we're trying to find out is dy over dt. Right? And maybe I should write feet per second. So we need to follow the steps, right? Step 1, write an equation that relates x, y, and 10. You think what that is? That's right, it's the Pythagorean theorem. X squared plus y squared equals 10 squared. Step 2, implicitly differentiate it with respect to t. 2x dx over dt plus 2y dy over dt equals 0. Right? Derivative of a constant is always 0. Step 3, solve for the thing that you're looking for. What are we trying to find? We're trying to find this. Okay, so that's going to be dy over dt equals, and pause, try to do it yourself. It's going to be negative 2x dx over dt divided by 2y. And of course, we can simplify that a little bit. Negative x over y dx over dt. Okay. Step 4. Plug in the known variables, or the known values, I mean. Dy over dt equals negative x over y dx over dt. And we know that, well, what do we know? We know that x equals 6, right? How do we know that? Well, they gave that one to us. What about y? Did they tell us anything about y? Well, not explicitly. However, we do know that 6 squared plus y squared equals 10 squared. And when you do that out, that means that y equals 8. Right, plus or minus 8, but you can't have negative length. So in fact, y equals 8. And of course, we also know that dx over dt equals 2. So when we plug all this in, this is going to give us negative 6 over 8 times 2, and that's going to give us negative 12 over 8, or negative 3/2 feet per second. Now, that's negative. Does it really make sense for our rate of change to be negative? Yes, it does, because the ladder is falling down. So the height of that top part of the ladder is decreasing. So it does make sense for the dy over d, or sorry, for the dy over dt to be negative. Okay. So note that in this case, the bottom of the ladder moved at a certain rate. The Pythagorean theorem, it did not actually move at a constant rate. That's not quite right. I should say a non-constant rate. Right? Note that the bottom of the ladder moved at a non-constant rate, right? Because it depended on the values of x and y. Right? But the Pythagorean theorem formula used 2 variables, not just one. That makes things a little difficult. Okay? Now, sometimes it really doesn't make sense to draw a picture. In fact, sometimes we're even given the formula, like in this case. I did swipe the formula from the book, but I swiped this part from the book, but I did swipe question 1 from just real life. All right, so right, we see our question. It doesn't make sense to draw a picture, but if you read the question, right, pause the video, read it, you can see that, well, if we just follow our formula or follow our, procedure, we just kind of copy down the formula. Right? So we just have this formula. Okay, no problem. And we're really asking for the change in weight, right? So it's good to write down what you're trying to solve, right? But whatever it is, we should note that it's going to be miles per second, right? Or MPS if you want, okay? That is what we're trying to solve. So step 2, implicitly differentiate. This is kind of nice because in this case, we don't even need to solve for dw over dt. It's just automatically solved for us. That's kind of cool. Note that w0 or w0 is a constant, right? Now, let's see. We're going to take the derivative of this. I don't know. Let's use the chain rule, right? So I'm going to say this is times 2 times the inside. Right, to the 1, whatever, right? And then times the derivative of the inside. Now, let's be a little careful here. We know that the top is going to just be, that's just a constant, right? So it's going to be 3960 over, but then, wait, no, we don't want, sorry, we need one more thing, squared. There we go. That's what it is. Now, why is it that way? Well, think about it. If you rewrite it like this, 3960 times 1 over 3960 plus h, or if you rewrite that as 3960 plus h to the negative 1, that's how you're getting that answer, okay? Okay, and so anyway, this winds up being negative 2w0, well, let's see. If we multiply, maybe just save some room, multiply it by 3960 squared, that's a little much. I can't do that in my head. 3960 squared. Okay. Note that that negative sign came up front. Don't forget about that negative sign, please. All right. And then we're going to get on the bottom 3960 plus h cubed. Right? All right, because you've got this and this. Become this. Oh, no. There we go. Okay. So then at this point, Well, we already did that. Step 4, well, I'm just going to cheat and do step 4 right up here. So I'll write C above. So what do we know? I guess we know, I should have written this up here at the beginning. We were going 0.55 miles per second. I should have written that. I should have written that D, oh shoot, I am totally sorry. I broke my own rule, you guys. I broke my own rule. You see what happened here? When we took the derivative with respect to t, we forgot to multiply by dh over dt. And so this is where I knew I messed something up. I didn't use the fact that we were going at 0.55 miles per second, right? I should have written this at the beginning so I wouldn't forget. Maybe I should write miles per second. Okay? So sorry about that. I forgot that when you take the derivative of the bottom, the derivative of 3960 plus h is not 1, it's dh over dt. So my bad on that. Okay? So anyway, now we're going to use the fact that dh over dt equals 0.55. And we're also going to use the fact that h equals 40 miles. Right? And so when we do this, we're going to get negative 2 times W naught times 3960 squared all over 3960 plus 40 quantity cubed. And just to simplify that a little bit, it's going to be negative 2 times 3960 squared W naught all over 4,000 cubed. All right, whatever that is. All right. Okay. Just doing sort of a back of the envelope calculation, it's roughly 1/2000th times, I was going to say roughly, it looks to me like it's roughly 1/2000 times W naught. Now that is not a final answer, right? This is the final answer. But just so you understand what it is, right? You can just put that into a calculator. Okay. Does the rate of change of a person's weight depend on their weight? Yes. Because the solution includes their weight, W naught. Oh, sorry, that should be a negative, by the way. I forgot about that negative. So once again, does the answer make sense? Should the rate of change be negative? Yes. When you go above the Earth's atmosphere, the further you get away from Earth, the less Earth's gravity is going to have a pull on you. So I guess that's dW over dt should be negative as h, or I should say, as dH over dt is greater than 0, because Earth's gravity gets weaker. All right, now one more example. Just one more example. This one we might want to draw a picture, right? Pause the video, read the example. Here's what we've got. Note that this is not drawn to scale. Doing my best here. Something like this. 6 feet right there. 30 feet right there. All right, let's see this situation right here. Right, we've got that. I get that. Whoop. Try that a little bit. Yeah. I'm close to that. Okay. So anyway, let's see if I can that a little... Oh, it's being a little annoying. Okay. Just want to be clear about what's going on. Whoop. Riveting stuff, I know. Okay, whatever. We're just going to leave it. There and there. Okay. Anyway. Street light is at the top of a 30-foot pole. 6-foot tall person walks away. So we'll say that this distance is x, right, between the person and the light. So we know that dx over dt equals 5 feet per second. How quickly is the tip of his shadow moving when he's 60 feet away from the pole? Well, the tip of his shadow, they mean this distance, right? We'll call that y. So dy over dt equals, Well, whatever it's going to be in feet per second. Note that I do include the units. Would I really knock you down from mastery to progressing if you don't include units? Probably not, but it's good habit to do so. It'll help your understanding. It makes the reader understand better, okay? So let's do this. I'm not going to enumerate this time. I'm just going to do it out in one shot, okay? State the formula that we want to know. Well, in this case, it may not be totally clear, but we're going to use similar triangles to relate these guys. So we know that y over... Let me actually just write that down, because that's use similar triangles. And we know that y over 6 equals x plus y over 30. And if we just simplify that a little bit first, right, I think it might help to simplify that out. We're going to get 30y equals 6 times the quantity x plus y, right? I just cross-multiplied. And that, in turn, implies that, so if we distribute this 6, right, we get, I think, and then subtract, we get 24y equals 6x. And then this implies that 4y equals x, okay? And actually, it might even be better to say, you'll see y in a sec, y equals x over 4, right? And the reason for this is because we're solving for dy over dt. So we want to solve for y because we know that we're going to, have dy over dx mean implicitly differentiate, right? So then it follows that dy over dt is going to equal 1/4 dx over dt, which we know, plugging in for 5 feet per second for dx over dt, is going to give us 1/4 times 5, or 5/4 feet per second. Okay? And I just want to point out, this is a little interesting, because here, this is constant. This depends only on dx over dt. Unlike our other examples, the setup for the problem may have been a little tricky, just figuring out what was going on. Using similar triangles may have required a little bit of cleverness, but the answer is actually the simplest answer we've gotten. A little bit interesting. That's all we've got.